Okay, let's hope it works. Good. So yeah, welcome everyone. This is the first online lecture. Due to my kid not being able to go to school today, we are having this in this format. As I said before, if you have a question, shoot right away. Just unmute yourself and pose your question loudly so I can actually hear it. If you don't like to be recorded, you can write it in the chat and Manuel will remind me. Okay, good. So last week in the lecture, we looked at augmentations. Augmentations are changes of data points such that we don't change the label. We had a look at several kinds of augmentations. And we learned that they're really important, not just in self-supervised learning, but really in any other subfield of ML, basically allowing us to improve performance and not having to label more data. To this end, augmentations have to be in a way realistic. So they have to reproduce the changes of data points that are to be expected under real-world conditions, and obviously they shouldn't change the label, otherwise they will not be very helpful. We've looked at pixel-level augmentations that we implement through convolutions, local geometric transformations or global transformations, and style transfer and GANs. And today, we will have a look at two very popular self-supervised learning algorithms, SimCLR and MoCo, who also rely heavily on augmentations, and we will see exactly how. So SimCLR and MoCo share a couple of ideas. Oh wait, there's someone in the lobby. Manuel, try. Ah, yeah, cool, that works. Thank you. So SimCLR and MoCo share a couple of ideas. They both project a sample. And by the way, these are always images here. A sample X to a latent variable H. And then this representation is then or can then be used, for example, in a linear classification task to probe whether or how good the performance is. But they train this network F using a nonlinear projection hat on top of H to project H into a representation Z, and Z is only used for training, and the whole head network, in this case, G, is thrown away after learning. So that's the same for SimCLR and MoCo, and both use in some way the so-called cosine similarity, which basically measures the angle between two vectors. These are the references, and yeah, let's dive right in. No, let's dive in right away. Okay, good. So SimCLR, this is an overview. Let me just switch this window away. Hide window. Okay. By the way, can you see my pointer here?
Yes.
Okay, perfect. So SimCLR uses augmentation functions and randomizes what they do. We'll have a look later on a later slide what exactly they do, but you can think of this as you know, one of the augmentations that we already talked about, so cropping, color jitter, and all these things. So given a sample X, we'll produce two augmentations of the same sample. Obviously, these are positives. And then we'll project them to a representation Hi and Hj, project them further into Zi and Zj, and only between these two we maximize agreement by applying the dot product again, but then normalizing by the length of these vectors, which basically means only the angle between the vectors is determining the value. Yeah, so one being perfectly aligned, 0 being perpendicular, and -1 being opposite of each other. Okay, so T will be reviewed further on a later slide. F is, as I mentioned, a network. G is also a network and is nonlinear, and we measure the agreement with this cosine similarity. And again, as I said, this whole head here is thrown away after training. Good. So the intuition of SimCLR is this. If I showed you one image and like a whole bunch of other images, it is very easy for us humans to determine which one is the one that we are searching for. So given a representation of this image and a representation of these, let's say, database images, which one this is simple for humans, but depends on how we represent those images. If I just took, for example, the pixel values in this, I don't know, couple of 100,000 dimensional space, it probably wouldn't be as easy a decision than using some better representations. And the SimCLR goal is to find exactly this good representation that allows a classification based on an input. Okay, so given this, which one is it? Okay, so in SimCLR, we could use many augmentations, most of which we already discussed. So taking a crop out of the original and sizing it to the original size, or interpolating the pixels in between. We could do cropping, resizing, and flipping, and all these things that you can see for yourself. I don't have to read them for you. But it turns out that in the end, we'll only use 3 of them, because the others don't really help much in finding a good representation. And we'll look at that also a little later. The paper proposes only cropping and resizing, color jitter, and smoothing, although I think the smoothing didn't yield that much of a performance gain. I think the most impactful ones were these 2, cropping and resizing, and color distortions. We can apply them sequentially, so first cropping and then distorting the color of the crop. And you can think of the SimCLR approach as using one of the augmentations in this branch here, in this arm of the processing, and then applying the second one to this in this branch. Okay. Implementation details. SimCLR uses like a common ResNet 50 for this function f here. And I don't know if you remember or who had a review of ResNet 50 yet. It's basically a sequence of these residual blocks, so convolutional layers with bypassing those, or with the input bypassing these blocks as residual connections, and then you have a couple of those, and in the end you have the average pooling and a fully connected layer, and the average pooling layer serves as our H, as our representation. The nonlinear head, G, is basically only applying ReLU to the first projection, and then projecting it a second time. Yeah, so simple, fully connected neural network here. As a loss, we apply the so-called info NCE loss, which looks a little different in the paper. They called it NTXend. I think the only difference is that in the sum here over all samples, we exclude k equals I in the denominator, and for info NCE, the equation looks the same, except that we do not exclude the k equals I. So, but the general form of this loss term here for a given combination of I and j, and in this case, these are the positive pairs. So who knows what this looks like? Let's have a little bit interactive here. Say again?
Softmax.
It looks like softmax. It is. It has the negative logarithm of it, so it isn't softmax. But it's basically softmax with coarse entropy. It's very similar to how we train classification networks in a supervised setting. Yeah. So this probability here is also scaled by this tau, which is referred to as temperature. So you can change these and alter the shape of the distribution that you create here. And you will see later how exactly the final loss is computed and what it does. But so we take these individual losses, Lij, for a certain positive sample, but we also iterate k over the entire batch, which has negative samples as well. And we compute the similarity. So S, let me just go back here for you. Oops. S is this cosine similarity. S between the ith input, so one of the augmentations, and all the k in the batch, among which one is j. So like a positive sample, but all the others are negatives. Yeah. Good. We then look at this. Yeah, I'm going to show that on the next slide. I think this is much more intuitive then. But yeah, we have a batch of n samples, and by the way, n is going to be huge. It's not just the typical 32, 64 or whatever. It will be in the thousands, but that is something for a later slide. So this is the algorithm as outlined in the paper. So we choose our hyperparameters, batch size n, a constant tau for the loss, for the info NCE loss. We decide for a certain structure of the encoder for the head. And that, I think, that's the augmentation, yeah? So which augmentation functions to take. Then we sample a mini batch. So samples like our dog and cat and birds and so on, and many. And for these, we do the following. We loop over them. We first draw two augmentation functions, t and t dash, and plug the first sample and the second sample into the augmentation through the encoder and through the head to obtain, well, our augmented sample, the hidden representation, and the Z representation for learning. And we do that, yeah, twice for the different augmentations. I just have to plug in my power. Sorry, guys. Bringing it here. So any questions so far? Okay. Yeah. So we have a mini batch of although it doesn't really, it's really not a mini batch. It's many thousand of those samples. We augment them, embed them, project them, and do it twice for the two different samples, coming from the same input. Yeah. And then we have, you can imagine, each sample comes in two versions, and we have n many, so we have 2 times n many in the end. Yeah. So we go through all of them and look at the pairwise distances. So we have a variable I and j running through all the 2n samples and all the 2n samples in like the matrix, in a matrix kind of fashion. We'll look at that on the next slide. And we'll compute the the similarity, the cosine similarity, and also this loss term with a small l, just as we just have seen on the previous slide. And then we compute the loss, which basically is summing up always the corresponding loss terms, so the individual loss terms for, so L 2k minus 1 and 2k is basically the first sample, or the similarity of the first sample with the second. And these two, you can imagine as being from the same picture, right? So we put them always next to each other, and then the next sample. So the first two are the augmentations, the two augmentations of the same image. Then the next two are the augmentations of the second image, and so on. So the similarity 1, so row 1, column 2 is the loss term, this one here, for the positive sample pair, and this one here is also the loss term for the positive sample, but the indices change. And so these aren't the same values as this. You have an idea why that is?
Because augmentations are switched on the two images.
Well, the augmentations are not the same. And also, if you look at this, so the similarity between I and J and the similarity between J and I should be the same. But in the denominator, we sum up over other similarity pairs. So first, in this, we look at the similarity of Si to all the others, and the similarity of Sj of the other augmentation to the other samples in the batch is computed here in this value, right? So we compare it to other. So we have one sample compared to all the others, and then we have another sample compared to all the others. So the denominator is different. So this value here is also different from this, and that's why we just take the mean or the sum of both. Yeah, and then we do that for all the samples, always adding these two values up, and that's our final loss. And then obviously we take the derivative, backprop it, and update our weights into F. Yeah. Oh, and G obviously too. Okay. So this is basically the summary of the algorithm. Who needs help here? Okay. Okay. So let's do a little example. We have a cat and a dog and the bird and the squirrel. And these are the two augmentations. So this is xi and xj. I think they had a tilde as well. For the different augmentations that we want to use. So for example, this is a crop, and this is a color jitter, this is blur and flips, and well, yeah. So the batch is 4, but we do have 8 samples. So what we do is I can even zoom in, cool. So what we do is we sort them, not sort them, but we, just think of them as pairs belonging together. Yeah, the cats, the dogs, the birds, and the squirrels. And now compute the pairwise similarities. So similarity between this guy and this guy, this guy and this guy. And for a given row in this matrix, the red ones here are the negatives. Yeah, obviously in the single loss term, the e to the similarity between the two pairs in the denominator, that's the positive pair. We need that to be as similar as possible. And in the denominator, we exclude this guy. Actually, we exclude this guy. But then we have many. So we want the denominator to be as, wait, this is the e to the, yeah, these should be as small as possible. Yeah. So we minimize the negative of this. Okay, good. So the final loss then is basically computed between these off-diagonal elements. But it isn't that we only use these samples, right? So in these values, we integrate information about the similarity of all the other samples as well. Okay. Yeah. So the cool thing about SimCLR is that it's really good. It creates representations that are really powerful compared to a supervised model. So what we usually do in a self-supervised setting is we train a linear classifier on top of H, like this. So some weight matrix that projects H into the number of classes that we have. So let's think of ImageNet, 1,000 classes output with a bias term, and that's our prediction. And we train these parameters, but freezing F. So we have thrown away G already, and then train a new classifier, basically only for ImageNet. on H, but F stays the same. Yeah. So the embedding that gives us H isn't changed at all. And the cool thing is that SimCLR outperformed the entire batch of competition here by quite a margin back in the day. But it appears such that we need a lot more parameters compared to the supervised baseline here. Yeah, so the supervised model, whatever that was, only needs 25 million parameters, and SimCLR in this best version here approaching the performance, so top 1 accuracy, so approaches the performance of the supervised model, but at the cost of having to train a model that is 40 times, oh wait, what is that? 16 times larger, yeah? But SimCLR, and that's true for pretty much all the self-supervised learning algorithms, they shine when you don't have that much labels. So the supervised baseline was trained here on 100% of the data. But what if we only give it 1% or 10% of the data? And a really drastic drop in performance can be seen in the supervised baseline, but pre-training SimCLR and then training the classifier with only the linear classifier only with the 1% portion of the training data gives us still an 85%, so almost double the performance as a supervised baseline. And this baseline grows in performance when we give it 10 times more, only a tenth of the available data, but also SimCLR representations are really good and get much better. So that was really impressive and kind of indicates in what kind of settings we want to resort to self-supervised learning, which is we don't have much data. Yeah, okay. So a couple of words with regards to the projection head. Why do we use a nonlinear projection head? Well, because it works best. So we want to, or the authors in the paper compared performance of a linear classifier using the representation that was trained with either no projection head, G, or with a linear projection head or the nonlinear projection head that we saw on the previous slide. So with no projection head, H would be trained as we saw before using H directly, right? So directly comparing the representations and computing the loss and so on, yeah? And so interestingly, we need some projection. If we increase the dimensionality of H, we kind of see some performance, but basically projecting H into a Z space in which we then learn, in which we apply the loss function, improves that at least by 10%. And a smaller boost, but still significant, is then obtained by using a nonlinear head. Yeah. Okay. So the interpretation is that the learning objective, so maximize similarity between positive pairs while minimizing the similarity or maximizing the distance between negative pairs in this kind of fashion, may discard information that is useful in downstream tasks. So, for example, if we rotate an image and we want to minimize we want to minimize distance or maximize the similarity between those two rotated versions of itself, we kind of lose information about how strongly these two versions were rotated from each other. So the augmentations are kind of a way for the network to learn something meaningful, but it also leads to forgetting something in these last two layers in case of the nonlinear representation, or sorry, in case of the nonlinear projection head. Yeah, so in Z, there's less information than in H, and so we can throw away that part and only take the representation. Okay, was that clear? I found that interesting because when I first read this paper and saw this architecture, I said, okay, why do they even use like another layer on top of this, or two other layers on top of this? Why don't they just apply the same logic, the same mechanism on the representations H? And well, that's exactly the reason, because Z is bad or not as good as it could be. So if we used it directly on H, H wouldn't be as good as it could be. And we would be having to extract something earlier in F to get something that is powerful. Okay. Now batch sizes. As I said, SimCLR needs huge batch sizes to learn good representations. So we, for example, compared here, or not we, but the authors compared batch sizes of 256 up to 8,000. And we see that in general, especially in the regime with shorter training times, we see drastic improvements when using huge batches. Yeah. In the end, and there's also like another plot in the paper for much longer training times. We see that in the end, even the large batch sizes kind of make a little dip downwards. I think in the paper they either use the 4096 batches or the 8000 batches for the plots that they produced. But they also had access to 128 TPUs. And yes, they were able to train it really fast, but that's nothing that we can do for two reasons. First, we don't have TPUs or not that many TPUs, and the GPUs that we have don't have enough memory. In the paper, they don't even mention memory requirements, which is a little odd because this is obviously one of the things that decides whether I can use it or not. But we'll come to this in one of the later slides because MoCo has quantified that. Yeah. And then augmentations. So I told you that given the many augmentations that we can do, we actually only end up doing 2 or 3. And this is why. So in many of these papers, you see ablation studies, ablation meaning we take away some parts and see how the performance drops to quantify how important that part was. And here they played around with combinations of two augmentations, the first transformation and the second, and them being cropping, cut out, color, sobel, noise, blur, and rotate. I think they're self-explanatory here. So crop and crop means they just crop once, but crop and cutout means they first crop and then they cut out something. And crop means also crop and then scale it back to the original dimensions. And what they measure here is again the performance of a linear probe, a linear classifier on top of the embeddings that we obtain after training. And we see that cropping and color combined stands out here. And that's why they use these. I think they used also blur, but yeah, we don't see the combination of three consecutive augmentations, but that's what they use. And the choice for color and crop is really based on this analysis here. They also say that they augment the color, so the color jitter, in a much stronger way than they would be doing in a supervised fashion. In a supervised setting, the color jitter that they introduced in SimCLR would even hurt the performance. So that's interesting. So it seems that cropping and color jitter is really important in a self-supervised setting, but the intensity, the magnitude of the jitter of the color needs to be higher. Okay. Okay, so that was SimCLR. I really recommend reading the paper. It's a well-written paper. They do a lot of different things, really systematic and lovely paper. I really recommend reading that. Okay. Now, MoCo. MoCo is short for momentum contrast, and it addresses a problem that we see in SimCLR, which is the memory requirement. So here they call it end-to-end because they basically train the encoder going through both branches of our two augmentations. And in momentum contrast, they basically only train this path. They backprop through this matrix here and train only the encoder, and they use another encoder, which I will come to in a second. But the interesting part here is that the memory requirement of SimCLR stems from the fact that we have this quadratic kind of loss size that goes back to the number of samples in the batch. Yeah, so this is 2n times 2n. This is n. This is n. And so to keep all the the activations from the forward pass really creates this memory requirement. And looking at this part shows you why MoCo is much more efficient. Somehow they reduce the affinity matrix, which you can think of this matrix that I showed you in the sample and the example with the 8 different or 4 different animals and 2 different augmentations. The affinity matrix here is much smaller because they basically have a long queue of negative samples and only a few, so the batch size here is only 2, only a few samples that they draw from the data set, and then compare like this. These are the positives, and all the rest are the negatives. The interesting part here is that they use an encoder that starts being a copy of this guy, but when training, we update the weights and biases of the encoder with backpropagation, and then copy the parameters over to this momentum encoder, but not in a copy kind of way, but in this momentum kind of way that I will show you in a second. The interesting part really is that this queue can be really long, much longer than the batch sizes were in SimCLR. So they don't really say in the first. So MoCo comes in 2 flavors. One is pre-SimCLR and one is post-SimCLR. And MoCo version 2 is post, obviously, SimCLR, and it is outperforming SimCLR. So that's why I'm putting this here. So they don't even say explicitly what the size of the queue is, but it is fixed and it's filled before we start training. But over the training course, we add more samples in there, samples that are encoded by the encoder that through training changes. So the samples, even if they would look the same that we add in the queue, are different vectors because the encoder has changed. But it changes a little slower because we basically update it using the parameters of the encoder, but we mix it with the old parameters. So you probably have already seen this kind of equation. So our parameter set theta k, so for this function here, is a number m, which is smaller than 1 and or between 0 and 1. So some portion of the original parameters plus 1 minus m, this data set, this parameter set, yeah, from the encoder. So it's basically mixing these two such that the relative weighting can be determined by m. So you can choose m to be 90% or 95% and 99%. Usually they're not much smaller than that. So only a small influence into the parameters of the encoder, of the momentum encoder, from the encoder's parameters, right? So there's constant flow, let's say, information, but since m is pretty high, the momentum encoder is kind of smoothing the sometimes really noisy trajectories of the parameters in the encoder. Yeah, so we update our momentum encoder by this beautiful kind of little mixing equation. And we keep a long list of, let's say, 65,000 samples as negatives, and then basically do the same as SimCLR. Yeah. So you can understand MoCo and MoCo v2 basically as SimCLR, but with a little tweak, little trick that allows us to reduce memory requirements here, but at the same time using many more negatives. And that's about the basic idea in MoCo. I also recommend reading that paper. So the MoCo 2 paper is really only 3 pages long because they basically reuse everything that they've written in the V1 paper. But they do share some more details. So basically reading MoCo V1 makes sense, and then reading MoCo V2 on top of that. This is a little summary of how these approaches differ. We haven't talked about the middle one here, which I don't think we will and we should, because it's so the memory bank is basically a vector store on disk. It's pretty slow, and the way they do it allows even taking more samples with less memory requirements. So it's basically rendering this approach unnecessary anymore. So this is SimCLR using the gradient flows into the encoder for both branches of augmentations, and sorry. And this is the momentum encoder using only this branch into the encoder, and then using this kind of mixing that updates the momentum encoder. Okay, MoCo v2 outperforms SimCLR clearly, but requires much less memory. So MoCo has a batch of 256, which is already smaller, or which leads to a much smaller memory footprint, even compared to SimCLR with the same batch size. And remember, SimCLR needs 4K or 8K, and that leads to a memory requirement that they estimate to be in the range of 90 to 100 gigs of VRAM, of GPU RAM, which is something that, at least in my group, we don't have yet. But yeah, so performance-wise, SimCLR is clearly outperformed with even smaller batches and training shorter durations. Yeah, okay, so in summary, SimCLR and MoCo are like prime examples of contrastive representation learners. I chose to bring those up in the first half of the semester because they really stand out as nice examples. Also, what are the problems in the field and what are solutions? They use both simple augmentations, which is neat because if we want to implement this, we really have to only focus on the core concepts and not on weird augmentation techniques. By the way, the SimCLR comes with an implementation of the authors. I think MoCo too, but I haven't looked at it yet. They use both samples in the batch or in the queue as negatives. So saying that positives are really much, there are really much fewer positives than negatives. Yeah? Negatives are much more numerous. Both employ the info-NCE loss, which is basically the softmax or negative loss likelihood of the softmax classifier, so softmax plus cross entropy, using the positive sample as a target class. Both require a best case nonlinear projection head that maps H to Z for training, but then we can throw away Z, or the function that maps H to Z, and only keep F that creates our representation. SimCLR is really simple. That's why it's called simple contrastive learning representation. Works well with huge batches. So if you have enough GPU memory, you can definitely go for this guy. MoCo, I think, is a little bit trickier to implement because it uses this kind of queue here, but it reduces the memory footprint and is a good alternative of SimCLR, even outperforming in this V2 variant, outperforming SimCLR. And that was the shortest lecture I've ever given. And I'm happy to answer questions. I'm going to stop the recording now, so don't have to be worried.
Maybe you can repeat a bit about projection head. Why do we need it in the first place? Because I don't see it clearly. Is it to reduce the number of parameters, or I mean, if it doesn't make any additions, why does it help? It's not clear.
Yeah. Wait. Here. So first, I think the first thing to notice is
we don't see the slide if you show them.
I am, but sorry. Can you see them now?
Yes.
Okay. So the first thing to notice is that the empirical results indicate that a projection head is better, that it does help the representation H to become more powerful for the linear performance, or the linear classifier performance. Yeah, did you understand this part?
Yeah, the empirical part is clear. Yeah.
Okay. Now the question is, why is that, or how do we interpret these results, right? And that's your question.
Yeah, the reason why does this head helps in learning? Yeah.
Yeah. Okay. So the interpretation that they offer in the paper is this: the learning objective. So basically, trying to classify the positive example. So contrasting the positive and the negative example using this loss that we saw, the influence loss. This learning objective leads to the projection head, the classifier, not the test classifier, but the function G, to remove information that may be necessary in the downstream tasks, for example, in the linear classification probe that we then use afterwards. Yeah? So, for example, if I had two versions of an image that are rotated from each other, and we map representations that still contain these rotational information, we map these representations into a space Z that makes them more similar. Yeah, these two Z's. We kind of lose information about the rotation, which may be still necessary or informative or useful in the classification tasks that we then do in analyzing the performance. Yeah, did you get it?
Yeah.
Or color information, for example, right? So we jitter the color, but the color of an object often gives away what it is, or the rotation too, right? So there are things that we do in order to create different views of a sample that but then we try to make them more similar. In this last step, we lose information that if we would do it directly on the representations that we use for the classification evaluation, for the linear classifier, these representations would lose performance because of this fact. So this is how they interpret this.
This head is trained as well, right?
What is trained?
The head, the function G is also trained.
Yes. Both F and G are updated in the training. So G tries to, I mean, you can think of this as one network, but we train, and the last layer is Z, and one of the previous layers is H. Yeah. So we don't really have to differentiate between them and call them different names. It's basically a hierarchy of representations that we train in the network. And the last layer is the one that we apply this optimization objective to, which means that the objective that we minimize here is best met, not perfectly, but best met in the Z representation. And if we go further, we likely have more information. Huh? It's not that it's compressed in the number of dimensions. I think Z and H are the same number of dimensions. It's really the information content.
Yeah, this explanation is clear. Thank you.
Thanks for the question. Any more questions?
What if we don't actually remove this G layer, the last projection head?
Then it would be the same or similar to using no projection head and using H directly, right? So we could formulate the loss not using Z, but H directly. Since they're the same dimensionality, we can directly, in the code, unplug or replace them. And then what we see is the performance drops. They don't even show the bar here.
Okay.
I think this is the most interesting part of this paper, really, of the SimCLR paper. All the other stuff is something that we already looked at before. Augmentations, contrastive loss, linear evaluation, all something that we looked at. The interesting part is that we don't take the last layer, we take the I don't know, penultimate or even 2 layers before.
Okay, yeah. Thanks.
And when the authors compared supervised learning with the SimCLR on reduced data set, when SimCLR outperformed, this picture, did they explain the reason for this outperformance? Because it's also not clear, as the architecture is the same, the data which is seen also the same. How SimCLR learns so much better?
I think it's a little unfair, because in this, the way I understand it is that the supervised baseline was trained from scratch. So it really has not seen all data and all labels. It just sees 1% or 10% of the data, of the labels. SimCLR was trained on the entire data set without labels, so it could see all data. And the linear classifier for the evaluation, right? So you always train a linear classifier on top of age. This guy has only seen 1% or 10% of the labels. But since for the supervised baseline, you can't train it with more data using no additional labels, yeah, it's kind of an unfair.
Yeah, unfair, true.
Comparison. But it's still interesting. So there are other things that also MoCo does with transfer learning. So you train a supervised baseline on dataset A, and then you fine tune it on dataset B, for example, using only portion of the labels. That's a much more fair comparison, but it's still interesting that Resident 50 can already be good with 10% of the labels, but the same amount of labels, using this representation learning, pre-training, gets you almost 13% or 12% performance boost. And in real life, there's so many applications and modalities. So not just image classification or so, in which you don't have that much data, or acquiring labels is so much more expensive. So this is really something, so self-supervised learning isn't some fancy kind of research topic. It's relevant in practice for so many different things. Because data is available for, yes, of course, for images, for example, because we have ImageNet, or even larger sets that Google curates and stuff, available for them internally only. But that's just images. I think there's, and even within, if you stay only within the image realm, medical images, for example, you always have, I don't know, data in the order of a couple of thousand or so samples. And that's way too little for deep learning. And so these things, SimCLR, CPC, and all these things are really a game changer. They really enable deep learning.
So even now SimCLR is cutting edge, thin in the field.
I mean, MoCo V2 has already has beaten it.
Yeah.
And SimCLR is really hard to train properly if you don't want to reuse the already pre-trained networks and you want to train it from scratch. Yeah, it's not going to work if you have like just a GPU, you know, in your home computer. And I think, you know, most of the community is like not in the long tail with a lot of compute. They're like in the I don't have that much. And yes, there are compute centers that we can apply to. Hey, we need your GPU cluster for that and this for that many days. And so yes, it's possible, but I think most of us try to find the sweet spot between computational and memory requirements and time also, right? So, and that's why I think SimCLR isn't that relevant, at least from my use cases. Maybe one anecdote. Have you heard about the challenge, the Vesuvius challenge that Youssef won? I mean, he didn't win yet, but there was like one of the phases, and he won one of the early phases. Got a second prize at least for decoding the scrolls that were buried under ash and lava and were hidden almost 2,000 years, and they CT scanned those scrolls. And so what do you do to train a model to segment those Greek letters out of those scans? There's no data. There's nothing. So what Youssef did is he didn't take SimCLR or MoCo. He took something that we will review later, and yeah, he won with that. So there's no training data at all. I mean, the training data that was provided was I think 7 scrolls that were only partially labeled. So it's a nice example. You know, it's one of those things that aren't really relevant for the world, for most of the world, but there's like a whole community like after the results of this competition, because it's so different from all the scrolls that had been found before, and people think there may be interesting stuff, historical stuff in there, and everybody is really excited. And yeah, reading those things without self-supervised learning wouldn't be possible, at least not in the extent that we've seen. Okay, guys, any more questions? Good.